Okay, what you're looking at right now is a test tube. That long piece that you see right there is actually lead. I liquefied it like a couple years back, and I poured it into a pitcher, and this is like the shapes that I would get. But anyway, the purpose of this experiment is to literally induce fission, not fusion, induce fission in lighter or in really heavy elements such as lead. And I just remade this video, and I'm using a clear test tube right now to show radiation damage. Yeah, I'm using lead because it's non-radioactive, and you could easily see the effects. So anyway, when I pump down, you will very quickly begin seeing phosphorescent effects on the glass and very quick radiation burns on the glass. And I don't know how bad the radiation actually is or anything, but basically I have the pump as the positive, which is supplying the ions, which are then accelerated and hit the lead metal. When they hit the lead metal, they knock off some of the lead atoms. When the lead atoms start circulating in the mixture slowly becomes more and more lead. Anyway, last time I did this, when I pulled out the lead piece, it was hot. And the power supply I'm using for the experiments is very weak, and I've never had an electrode get hot from any sort of plasma experiment I've ever done before. So that was a first, and I think strongly signifies that indeed I am inducing some sort of fission type reaction, and it's really incredible. So I'll go ahead and I'll plug this in real quick, and I will start videotaping for you. Okay. Okay, so you can already see that. Watch the glow increase. As like right now, it's actually like a very purplish color. The lead is looking a little bit red, and you can yeah, the lead's looking reddish, and I'm already seeing some greenish colored glowing. And I really wish you could see this as I'm seeing it right now. It looks totally different in the video than it does in real life. Yeah, the lead is like a dark reddish color, and I'm not seeing any radiation type burns just yet, but could very well be a possibility soon. Hang on. Like you can see some of the impact points where you see little sparks. That's like points where an ion literally impacts with the lead and induces a small plasma around it. Yeah, I should probably get some serious radiation stuff. Keep in mind this was a very clear thing, and it doesn't actually look like I'm pumping down to that low of a pressure. Yeah, hang on. Okay. Sorry, I had to rearrange that. Yeah, you can see just through the glass right here some of the convection of the like of the light from the X-rays, and you can actually start seeing some of the, well, you can't see it in the video, but in person you can actually see some of the burning effect kind of taking place. And this is much more this is much more luminescence than I've ever actually witnessed before from this kind of thing. So I'm assuming, and it's a pretty big assumption, but I'm assuming that this has actually been successful. I seriously, I think I'm getting more optical output right now than I'm actually even putting it electrically. And the majority of the optical output would be in an X-ray range. That just means that the phosphorescence of the light alone could be more than what I'm putting in. So I mean, I don't know what kind of radiation I'm probably getting right now, but I mean it's very, very cool. on 1 second. There we go. Okay, I'm pulling it back. Hold on. There we go. Yeah. Getting a little bit more impact. It's hard to be a cameraman and a scientist at the same time. I don't know if you can see any of that. Yeah, look at that line right there. That's pretty cool. Yeah, but I will show you the radiation burns in a minute. Yeah, just look at that. I'm sure this glass has got to have some somewhere. I mean, this reaction doesn't look as fierce as the one before it that I just did. It might be because of an air pressure problem. I might have had a lower pressure on the last one, thus a longer mean free path, meaning more collisions on the actual surface, which is what I'm going for. So I don't know for sure. Alright, I'm going to go ahead and turn this off. Okay. And I want to just, hang on 1 second. I'm going to hold the lid real quick. Oh yeah, it's definitely warm. Definitely. I mean, it's not hot, but it's warm. So we'll take the glass. Wow, there's actually like barely any. I really thought that there'd be a lot of radiation damage on it, but actually it looks totally fine. That's so weird. There's a little bit. Hang on. I don't know if you can see that. Yeah, that definitely was not there before. I don't think I can scratch that off. I don't know. That's really weird. I could have sworn that, well, the last one, here's the last one. This is, hang on 1 second. I tried to wash the last one out because it was just, I thought it might have been dirt last time, but this is where I had the electrode. Hang on 1 second. Let me try and clear it out so you can see a little bit. See that brown mark right there? That is actually just, that's where I had the electrode, right there, and it was like glowing so brightly. There were so many reactions just taking place right there. And that's the opposite side where the ions were coming out. So, and the glass is very foggy, and I'm pretty sure that means some sort of, I think that the X-rays, or I don't know if it's X-rays or actual ions, when they impact the glass, they might change the atomic structure of the glass possibly into something like maybe some of its constituents, like maybe carbon or just hydrogen or maybe just oxygen. I don't know what, or no, glass is more like silicon. I don't know. Anyway, it probably breaks them up into individual compounds and stuff. Okay, well, that's all.